which is 2 lambda min.
Right, so this is lambda max over 2. Okay, and so we have that nu is C over lambda. So delta nu would be C over lambda A minus C over lambda B. And so in this case, let's let lambda A be the smaller of the two, so it's positive, so we have C 1 over lambda max over 2.
Okay.
And so that's what, C 2 over lambda max?
Okay. So that's delta.
Or no.
Wait.
That's lambda max. 1 over lambda max. Well, C over lambda max. Yeah.
Okay.
Okay. And then coherence length is C over delta nu.
And then, okay. So like I thought that it would end up be, so I thought delta nu was equal to C over delta lambda.
Oh,
So,
no.
essentially,
No,
yeah,
no,
that's
no,
what I thought.
Yeah,
Okay.
that's why I did that
Oh, that's-
differential last time,
That's what, yeah.
is so that,
Okay, that's
No,
what I thought.
that's not the
That was the
case.
complete, okay.
yeah.
Gotcha.
Oh. Okay. So you want to jot that down real quick and turn it in?
Yep.
I have one other question for you.
Yeah.
In problem 3, where you're dealing with the two waveforms that are orthogonal to each other.
Okay.
At some point, I was able to intuit that when they are orthogonal to each other, it means the phases offset from each other by pi. But as I keep thinking about that, why isn't it pi halves?
Well, so the relative phase of the y to the x component is different by pi, or it could be orthogonal.
Okay.
And you're thinking two orthogonal vectors, I mean, they're orthogonal by 90 degrees.
Yeah.
But we're talking about complex quantities, not, well, yeah, I mean, we could try to draw it out.
Could we? That
We
might help
could,
out.
but there's a lot I want to cover today. So I
Gotcha.
recommend,
I can do it afterwards.
yeah.
Okay.
Yeah, and I'm gonna have to leave real fast. Let's just stick this because I've got a teleconference at 2.
Okay.
So Yixon. Let's see. Clayton. And Les. Here you go. Let's just do it this way. And Jace. Go. Ivan. There. Carlos.
Are you posting solutions on LearningSuite? Or?
No, it's just here.
Oh, okay.
Zach. Mark. Go. Alex. There you go. David. And Kurt.
Oh, she just turned it in? No?
No, that's number 1.
I grabbed
Oh, that is number
Lal and I with one of these.
Oh, sorry.
Yeah. We both still had our assignment because we were doing one of the book problems, and then just like, you're going to give them full credits.
Oh,
I have it if you want to see it.
No, we're good. We're good. It's fine.
Let's see.
The one is number 5. The one in question.
Yep. Okay, so I got all the homework 2s, right?
Okay.
yanked it.
Okay, so last time talked about Jones matrices for optical elements. We looked at Jones matrix for polarizers. We looked at cross polarizers. We looked at 3 polarizers in a row, rotated by 45 degrees, relative to each other. Saw that light passes that. And so today what we want to do is talk about waveplates. So, let's define what we mean by a waveplate, and that means we're going to have to take a little excursion into anisotropic materials, but we're not going to go too deep into it, but just enough to kind of give it a flavor. So, a waveplate, also called a retarder. So if I set up the coordinate system, so as always, plane wave propagating in z direction, and here's the x and the y axes, and then I draw a wave plate in here, something like that. Then a wave plate has something that's called a slow axis, so s-axis, and a fast axis. And what we mean is that for light that is polarized, linearly polarized along the fast axis, it travels fast. If it's linearly polarized along the slow axis, it travels slow, relatively speaking. So evidently what that means is that linearly polarized light along the fast axis sees a refractive index NF, and along the slow axis sees a refractive index NS. And we have that NF is less than NS because linearly polarized light along the fast axis travels faster than linearly polarized light along the slow axis. Okay, so what does that mean? Well, if you think about it, if I had linearly polarized light along the x, say I had a component like that, and linearly polarized along the y, and they propagate through here, then along the y is going to come out ahead of what's along the s, or the x. So I'm going to change the relative phase of the two components, the y compared to the x. And we already know that what determines polarization? Well, the relative phase and the relative amplitude. So this won't affect the relative amplitude, but it directly affects the relative phase. So this gives us the opportunity to convert one polarization state into another polarization state, depending upon how much relative phase we shift the y compared to the x-axis.
Is that just based on how big the wave plate it travels through?
So it's dependent upon the difference between these, so let's say NS minus NF, times the thickness of the wave plate. And then the other thing is it also depends upon what wavelength is propagating through it.
And this is by definition anisotropic then, yeah.
Yes, so this is an anisotropic material. It's the only way you can do this is with an anisotropic material. So we need to talk about anisotropic materials, and it's a vast topic, and there's a lot that goes into it, but we only want to hit the barest minimum that we can get away with and still have, or to give us kind of an understanding of how this works. And to do that, I'm going to introduce something called the index ellipsoid. I'm not going to tell you where it comes from, how you derive it, any of that stuff. I'm just going to say what it is. And basically, if we have some coordinate system, we have some coordinate system, and we have some crystalline material. So in a crystalline material, the atoms are ordered. They're not like an amorphous material where the atoms are unordered. So if we have a crystalline material, then it's possible that the material is anisotropic. It's not guaranteed, but it is possible. If we have an amorphous material, then we'll never have an anisotropic material. So let's say that we have some crystalline material and these axes are ordered relative to the crystal lattice in such a way that if we plot the refractive index, it looks like an ellipsoid, and we can write down the equation defining that ellipsoid as x squared over nx, actually let's do quantity squareds, plus y over ny, quantity squared, plus z over nz, quantity squared is equal to 1. That defines our index ellipsoid. And if we had an isotropic material, then nx would be equal to ny would be equal to nz, and typically we just call it n, refractive index. Now, there are various types of anisotropic materials, and we want to talk about birefringent materials, meaning that it's anisotropic, and a specific type, we want to talk about uniaxial birefringent materials. And in the case of a uniaxial material, then what we have is that nx is equal to ny, and we typically call that the ordinary refractive index. So the O here is for ordinary. And nz, we typically call that ne, where E is for the extraordinary refractive index. So for a uniaxial material, we have an ordinary refractive index and an extraordinary refractive index. Now, there are two types of uniaxial materials. There is positive uniaxial and negative uniaxial. For positive uniaxial, what that means is that the extraordinary refractive index is greater than the ordinary refractive index. So an example of a positive uniaxial material would be something like quartz, which is a crystalline material of silicon and oxygen, so silicon dioxide. In the case of quartz, we have that the extraordinary minus the ordinary refractive index is 0.009. So it's a pretty small refractive index difference between the ordinary and the extraordinary refractive indices. There are others, zinc sulfide, and a bunch of others. In the case of an isotropic material, glass would be an obvious isotropic material. But it turns out diamond is also isotropic, even though it's a crystal lattice. But that crystal lattice does not give rise to any asymmetry in the refractive index, therefore it's an isotropic material. Likewise, silicon, also a crystalline material, but again, there's no asymmetry to give rise to anisotropy, so it's an isotropic material. Gallium arsenide, cat telluride, also crystalline materials, but isotropic. So just because a material is crystalline doesn't mean it's going to be anisotropic. It could be isotropic. But if a material is amorphous, then it's always isotropic.
Is there like a point at which this difference between the NE and NO is just so small to consider it isotropic, or is it that it's like they're all exactly the same?
Yeah, these are all exactly the same.
Okay.
Yeah. Yeah, and then as to whether something that is uniaxial, you could consider it isotropic, then it gets back to your application
Okay.
and the geometry and the sizes and everything. Okay, so in the case of a positive uniaxial material then, we can draw the index ellipsoid. And in the z direction, it's going to have a distance NE along the z-axis. And for the x and y axes, it's going to go a distance NO. So if I try to draw an ellipse, you know, it's, I don't know, something like this. And in this plane, it's a circle. But in this, you know, in the XY plane or the rather the XZ plane or the YZ plane, it's going to look elliptical. So it's going to be an ellipsoid. So that would be what the index ellipsoid looks like for the case of a positive uniaxial material. And there's a particular way that you use the index ellipsoid to figure out what the refractive indices are and what the eigenpolarization states are for light propagating through the material. And it goes like this. The first thing you do is basically draw the direction of propagation, which is just the direction of the wave vector. And then you draw a plane that's orthogonal to the direction of propagation, and it goes through the origin. And then you look at the intersection of that plane with the index ellipsoid. And that intersection is, in general, an ellipse. And so you look at that ellipse, and I'm not drawing it because it'd be painful to try to decipher my 3D drawing. But we're going to do some cases in just a minute. And it turns out that for this ellipse, the semi-major and semi-minor axes are the eigenpolarizations or directions of the linear polarization states that are the eigenpolarizations. And then the 1/2 of the semi-major and semi-minor axes are the refractive indices, column N1 and N2, that those polarization states see. So that's generally how you use an index ellipsoid, but we're not going to worry too much about that because we're going to do the following. We're going to restrict the direction of propagation such that it's, actually let's put a caret on this, so this is just a unit vector in the direction of propagation. We're going to say that it's going to be either in the x direction, the y direction, or the z direction. And with that restriction, life suddenly becomes extremely simple. Yeah.
Could you read what phi says?
One half of the semi-major axis of that ellipse
Okay.
is N1, 1/2 the semi-minor axis is N2.
Okay.
So the two polarizations that or rather the refractive indices that the two eigenpolarizations see. Okay, so let's just consider,
Excuse me.
Yeah.
What is the second part in second case? After drawing the plane?
goes through the origin.
Oh, okay.
Yeah. Okay. Okay, so if we look at the case where the direction of propagation is x hat, so number one, draw k, well, okay, it's just an x hat. Figure out the plane that's perpendicular to that and goes through the origin. What plane is that? The plane that's perpendicular to x and goes through the origin is just the YZ plane. So now we can draw that YZ plane. It's just an ellipse like this, right? And this is NO, and that's NE.
And it just so happens, that's what N1 and N2 are, or sorry, it
Yeah.
happens at N1 and N2.
So for 4, the eigenpolarizations are, first, a linear state that's in the y direction, because that's the direction of the semi-minor axis. And then the other is linear polarization in the z direction, because that's the direction of the semi-major axis. So what that means is that if you have z-polarized light propagate through this material in the x direction, then that z polarization will not change. That's what an eigenpolarization is. It does not change. It only picks up phase as it propagates. Likewise here in the y direction, that linear state does not change as it propagates through the material. It only picks up some phase. How much phase does it pick up? Well, depends on what the refractive index it sees. So what does it see? In the z direction, that linear state sees a refractive index ME. The y state sees a refractive index NO.
Now, if you weren't linearly polarized, then it would change the
Oh,
polarization.
yeah, big time.
Okay.
And that's where we're going,
Okay.
because that's what that is.
Gotcha.
Yeah, Jason?
Well, even if you're linearly polarized, just in some mix of x and of z and y, right, then it would also change the polarization.
Yeah, it'll change the polarization. Yeah. Okay, so second case, if the direction of propagation is y hat, what's the plane? Yeah, so it's going to be the xz plane. And basically it's the same picture, except instead of instead of y, that's the x-axis. Nothing's changed. Okay?
So how did we know the shape to draw on our YZ plot here, or our
Here?
ZX plot? Yeah.
We just know that the intersection of a plane that's orthogonal to the direction of propagation.
So we were already given that index ellipsoid.
Yes, so we have some index ellipsoid,
then
and
we
it's
just
positive
slice it
uniaxial, so this. Yeah. Okay, so the third case is that the direction of propagation is in the z direction. And then what does the index ellipsoid look like? It's a circle. So the plane is the xy plane, and it's a circle, NO, NO. So if I have light that's propagating in the z direction, what does this uniaxial material look like?
Any other material.
Just looks like an isotropic material. Because it doesn't matter what polarization, what linear polarization you have, X, Y, or anything in between, it's always going to see just refractive index NO. Okay, so that's a positive uniaxial material. Let's do this. Before we go there, let's kind of draw this to a conclusion. So really here, all that matters is the z-axis direction. Because the x and y axes, if I have light propagating in x, same thing as if light's propagating in y. It's just this picture, right? Or if I had light propagating, in the XY plane in some other direction, it's still just that picture. It's only when I propagate in the Z direction that I have that picture. When I restrict myself to these three directions. So what that means is that I can take the Z-axis and just call it the C-axis and not worry about the X and Y directions. Meaning any rotation about Z, it just doesn't matter in terms of optical properties. So if I had a plate of this positive uniaxial material, and I specified that the C-axis was in that direction, then I could put an axis here and an axis here, and I would know that those are the eigenpolarization state directions for linear polarization, and that light linearly polarized here, what refractive index is it going to see? MU. And light here? NO. So here I'll see refractive index ME, here I'll see refractive index NO. So light polarized in this direction or that direction, which is going to have the faster propagation velocity? NO, because it's smaller, because we have a positive uniaxial material. So that means this is the fast axis, that's the slow axis of our waveplate.
So is that how waveplates are usually specified with the C? Like there?
Yep. Just specify the C-axis, and then you add whether it's positive or negative uniaxial, and then you know everything in terms of orientation.
So by specifying the C-axis, you're specifying the Z-axis, right?
Yes.
So you're saying that this is either case 1 or 2,
Yes.
not case 3.
Correct.
Okay.
Yeah, David?
I was gonna say, does the C stand for anything in this case?
No, it's just, well, if it does, I don't know what it is. It's just by convention, it's just always called the C-axis. Okay, so that's positive uniaxial. We could have negative uniaxial, in which case NE is less than NO. And some examples of that, calcite. Calcite is really nice because NE minus NO is minus 0.172. It's huge. Yeah. So that's why you like calcite. Calcite is calcium carbonate. And where do you get calcite from? Basically the ground. You have to mine it, find something that's really clear, cut it just right, and voila, now you have a calcite waveplate. There are many other materials, though, that are negative uniaxial. Lithium niobate is negative uniaxial. And barium titanate, also negative uniaxial. KDP, potassium dihydrogen phosphate, also negative uniaxial. KDP, if you have a green laser pointer, you've got KDP in your laser pointer. Because it turns out it's also a nonlinear material. And that's how you get the frequency doubling. We can talk about that later, but how those things work. Okay, so if we draw the index ellipsoid, then basically it's kind of a squat, squished sort of ellipsoid because NE is less than NO, but still in the XY plane it's circular. So basically everything we just said over here And number 3, it's the same except NE is squished and smaller than NO. So if I have a wave plate made out of calcite, say, and I specify the C-axis in that direction, then I know that this is going to be NE, this is going to be NO, I know what the eigenpolarization states are, and the question is which is the fast axis, which is the slow axis.
Yeah, and
Yep. So this is the fast axis, that's the slow axis. Okay. All right.
So, question, is there, conceptually, at least in my mind, it feels like, if you're just gonna have two squares that were wave plates, the application of the two is gonna be similar if you just rotate one 90 degrees.
Oh, yeah. Yeah.
so
So,
if you had a wave
what's-
cube, you could just pick a side and it would be one or the other.
So what would
Yeah.
be the advantage of choosing one over, or a positive uniaxial over a negative uniaxial?
there is no advantage.
There's not, okay.
Not in terms of its basic function. The advantages go back to secondary considerations, secondary effects. So, for example, if we did quartz, then we'd need a much thicker slab than if we did calcite.
You just have to know which way to orient it.
Yeah. Yeah, once you specify the C-axis and you know whether it's positive or negative, then you know how to orient it. Yeah. Okay. So, having said all of that, let's go back to our drawing here. And along the slow axis, we're going to have, let's just call it N slow. Instead of NE and NO, it depends on whether we have positive or negative uniaxial as to whether one's slow or one's fast. So let's just relabel the refractive index to say that along the slow axis it's N slow, along the fast axis it's N fast. Then in that case, yeah, let's go over here. We need to know what is the effect of the wave plate on particular polarizations. Or in other words, what's the effect of that wave plate? How can we write the effect as a Mueller matrix, or rather as a Jones matrix for that wave plate? So basically we know that if the light is linearly polarized in X, it's going to see a refractive index NS. If it's linearly polarized in Y, it'll see a refractive index NF. And as it propagates through the wave plate, what will happen in either case?
We'll slow down a little.
Yeah? It'll, which is the same thing as saying it'll pick up some phase. And will it pick up positive or negative phase?
Well, it can never go faster. It can never go faster than, I guess it depends on that goes initially propagating.
Yeah, so let's think about it this way. Let's write down the complex amplitude vector for a plane wave propagating in the z direction. And let's maybe pick, I don't know, the x-axis first. So what would be our expression for the complex amplitude vector of that plane wave? Okay, so what information does this have in it?
Amplitude.
As an amplitude, so what symbol do you want to use for the amplitude?
Use E naught.
You not? Okay. What else does it have in it?
E to the
Okay, I heard a phase. So e to the j phi, fine. I heard polarization. So what's the polarization?
J or A.
Well, p hats in general I mean, the polarization has to be a vector, right? And we said this was linearly polarized in what direction?
See?
Propagating Z.
Oh, sorry.
It's
Or-
X.
We said it was linearly polarized in the X direction, so the polarization vector is just X. And then there's a spatially dependent phase term. What's that?
E to the negative J.
E dot.
Is it just gonna be JX?
JKZ.
Well, it's propagating in the Z
Yeah,
direction.
yeah, JKZ.
So e to the minus j k z. Okay, so let's take our wave plate, and let's say this is the entrance to the wave plate, and that's the exit of the wave plate. And we have a z-axis going through here. And let's say that we want to specify the complex amplitude vector right here at the entrance. Is this the complex amplitude vector at the entrance? Could be. Just depends on how we define things. Let's say that at the entrance we have z equals 0. And let's just say that our phase here was 0. It's arbitrary. Let's just say our phase was 0 at the entrance. So what's the complex amplitude vector right there?
E naught X.
E is E naught x hat. Yeah, can't forget the hat. It's a vector. Okay, what's my complex amplitude vector right here at the exit?
It's gonna be some distant Z still.
Yeah, let's say that this thickness is, I don't know, L.
Okay.
So we'll have some
E
initial
naught
phase.
x hat e to the minus j theta.
So E naught x hat, then what?
E to minus j theta.
E to the minus j k L. That's it. We propagated a distance z that is L.
What about the phase?
So what about phase?
Well, let's just set it equal to 0. Or let's not. Let's say it has some phase.
Well, I mean on the second expression.
And then it'll
Isn't there
have,
an increase in
it'll
phase?
have the same phase over there.
Oh, there's
I mean,
no.
it's an overall phase that it already has when it gets here. And then we pick up some additional phase as we propagate. And the additional phase, we get it from that term.
Oh, okay.
Propagating
so, okay,
z
gotcha.
equals L. So that's that phase we pick up from propagating from z
Okay.
equals 0 to z equal to L.
All right, that makes sense.
And whatever phase we had coming in, that just adds to whatever we pick up.
All right.
In which case, it doesn't matter.
Yeah.
It's just some overall phase.
Okay.
We don't really care about it. So the amount of phase that we pick up in propagating from here to here is what? KL. So the phase is KL. Now K is what?
That
Yeah, we can write it different ways. We can write it as omega over C times refractive index. What's the refractive index in this case?
NS.
NS. So times L. We could write it that way, or we could write it as 2 pi over lambda. But what lambda is this? It's the wavelength in the medium.
Mm-hmm.
The wavelength in the medium is what?
Speed of light over n.
Well, is what in terms of the wavelength in free space?
It's n not over n times the speed of light.
It's the wavelength in free space divided by whatever the refractive index of the medium is, which in this case is ns.
Times the.
So if we substitute in here for this, then what we end up with is ns 2 pi over lambda naught. And omega over c is 2 pi over lambda naught. So either form is totally equivalent. Yeah.
So I'm confused on what NS is. I think I missed something.
That's the refractive index
In the slow
for
axis.
light that's linearly polarized in the x
Oh,
direction.
so just because it was in the X, we just call it that.
Yeah. So bottom line is, we just picked up this much phase. The only thing different between this expression and that expression is e to the minus j that much phase, right? So that's how much phase we picked up in propagating through the wave plate for light polarized in the x direction or the slow axis direction. Yeah.
So how is K defined as NS times omega over C?
So we did that early on.
Oh, that's a wave number, right?
Yeah.
Okay.
Exactly. Okay, so this is linearly polarized in the x-hat direction, which is the slow direction, slow axis. If we did linear polarization in the fast axis, which is y-hat, what would be different?
Just the amount of phase.
Just the amount of phase. And in that case, the amount of phase would be NF omega over C times L. Right? So that's it. Okay. So that means we can now just write down what the Jones matrix is. So the Jones matrix for this wave plate is what? If we're linearly polarized in X, how much phase do we pick up? So we have e to the minus j and s omega over c L. And this term, what does it mean?
How much phase accumulation in that one direction, the x direction?
Well, it's, if you think about,
That's like the amplitude.
this multiplication, that's, let's say, WXX, WXY, WYX, WYY, times, let's just call this JX, JY. And if we multiply this out, we have WXX, JX, plus WXY, JY, WYX, JX, plus WYY, JY, and that's the polarization state that's created, right? Okay, so what does this term mean?
It's like kind of like the contribution to y from going in the x direction, I guess, or something.
Yeah, exactly the opposite.
Okay.
It's how much of the original Y state ends up in the final X state.
Yes, which is 0 for us, right?
Precisely. It's 0. Why is it 0?
Because we defined it that way.
Well, it's that,
Just the nature of the material.
yeah, I mean, if we start off with some linear polarization in Y,
It stays in y.
that's an eigenstate of this thing. It stays in Y. So by definition, that's 0. How about over here?
Also 0.
Also 0. And then here?
It's the other one.
Yeah, we pick up the phase and F omega over CL. Okay, so now we know what the Jones matrix is for a wave plate. And do you understand how we got here? It basically says something really simple. And the really simple statement is, the X component picks up this phase, and the Y component picks up that phase. End of story. That's all it says. Okay? So, now that we've got that straight, let's see how it works out.
So
This Jones matrix we've created won't change regardless of whether we're sending in linear or circular polarization.
Yeah, it's totally,
The effect will change, I guess, but
yeah,
that
the,
matrix will not.
correct. The exit state will depend on what the entrance state is by this matrix multiplication. Yes, exactly right. Perfectly right. Okay, so let's write the phase difference between these two things. And let's give it a name. Let's call it capital gamma. And in that case, we have ns minus nf times omega over c times now. And this is called the phase retardation. And then we have the average phase. And the average phase, let's just call it phi. And that's going to be 1/2 ns plus nf omega over c L. And then what I can do is I can rewrite this Jones matrix as the average phase times a matrix that contains the relative phase difference. And so that would be e to the minus j gamma over 2, 0, 0, e to the minus j, or rather plus j, gamma over 2. So now, all we've done is we've just taken this, and we said, hey, let's pull out the average phase between these things. If we pull out the average phase, then that leaves us with the e to the minus j gamma over 2, e to the plus j gamma over 2, where gamma is this phase retardation. It's the phase difference between the two. Okay? All right. Now, notice, this is an overall phase term. And normally, we just don't care. So usually, we'll just toss this because we don't really need to track the overall phase because it never affects anything. We'll see why when we get to interference. So usually, we write the Jones matrix for a wave plate as just this. And we don't. We just get rid of the overall phase. Okay, so another thing to be aware of is that this phase difference, ns minus nf, we look at the magnitude of that, that's usually much, much less than ns or nf, as we saw for the case of quartz. It's really small. Calcite, even, it's still pretty small compared to the refractive index. It's about, 10% of the refractive index. So usually this is true. Okay, so now what we want to do is one further thing, and then we'll start doing some specific wave plates and what they're used for, which turns out are really useful. So let's look at a rotated wave plate. So we have our x, y, and z axes. And let's say, there's x again. Let's say that we rotate the slow axis here by some angle beta. So that means the fast axis is out over here. This is orthogonal. And, once, what I'm going to do from now on, rather than draw a rectangular block like this, I'm only going to draw the slow and fast axes, because that's the only information we really need. So, the matrix for this is going to be, first of all, rotate by an angle beta to get into the local coordinate system. And then we have the Jones matrix here for the wave plate. Yeah, and then we rotate by minus beta to get back into our coordinate system, our XY coordinate system. Okay. And then just another point is that this matrix here, the rotated wave plate matrix, is a unitary matrix. What that means is that if I take the Hermitian conjugate of the matrix, multiply it by itself, I will get the identity matrix. So what do we mean by Hermitian conjugate, and why is it important? Hermitian conjugate just means that if I take the Hermitian conjugate and I look at the ijth component, it's equal to the jith component of the original matrix, complex conjugated. So it's basically, if I have some matrix, I've got a diagonal set of elements, it's just swap across the diagonal, take the complex conjugate. That's all.
Conjugate transpose.
Conjugate transpose. So that's what a Hermitian conjugate is. Why do we care? Well, it turns out that unitary matrices have some really interesting properties. The relevant ones for us are that they are, well, a polarization state that is, well, a pair of polarization states that are orthogonal. If we cause them to undergo a transformation described by a unitary matrix, then the polarization states that come out will still be orthogonal, which is quite useful. And the magnitude of whatever goes in stays the same. That's also useful. But just be aware that this rotated wave plate is a form of a unitary transformation. But we're not going to really get too far on that. Okay, now to some actual wave plates. So the first thing we're going to do is a half wave plate. And I'm just going to call it HWP for half wave plate. In the case of a half wave plate, the phase retardation is pi. So we already saw that the phase retardation is ns minus nf omega over c times L, or we could write it as ns minus nf 2 pi over lambda naught times L. So let's look at these things here, this equivalence. The pi clearly cancels, right? And so we can solve for the thickness of the wave plate. That's going to be lambda naught over 2 times 1 over ns minus nf. So that's how thick I have to make that wave plate in order to have a pi phase retardation. And because this is lambda naught over 2, that's why we call it a half wave plate. The other reason why we call it a half wave plate is that to get a phase retardation of pi, we basically need to have the equivalent of a half wavelength of optical thickness difference. Okay, so in that case, the Jones matrix for a half wave plate is going to be, just looking at this, e to the minus j pi halves 0, 0, e to the plus j pi halves, which is just minus j 0, 0, j. Which is, I can just pull a j out, right? And that leaves me with a minus 1, 0, 0, 1. Right? Ivan, what's the question?
How do we get that matrix at the
This one?
top? Yeah.
Right here. And we just said, oh, gamma is pi.
Oh, gotcha.
Yeah. Yep. So, and then j, that's just an overall phase term, right? Throw it away. So, generally we just write the Jones matrix for a half wave plate like this. So that's a really simple matrix, right? Okay. Well, what if we rotate it? So let's draw this. So we have the x-axis, y-axis, and let's rotate the slow axis by beta. And then evidently the wave plate, Jones matrix, when rotated by an angle beta, is just going to be rotation matrix of beta times this W naught half wave plate, and then rotation matrix of minus beta. Just the usual thing. And if we plug in and do some algebra, which you'll do in a homework problem, what you find is that this is minus cosine of 2 beta minus sine of 2 beta minus sine of 2 beta and cosine of 2 beta. So that's what it works out to be. Okay, now let's do an example. Okay, let's go back over here. So for example, let's say we have a rotated half wave plate with x hat linearly polarized light instant. So here's z, x, our slow axis is rotated by an angle beta. Here's our fast axis, and then the linear polarization state coming in from the left is x hat linearly polarized. And what we want to know is, what's the output polarization state? So the output polarization state is going to be this half wave plate rotated by beta, Jones matrix, times this linear state, and this linear state is just L hat x. We defined that before. And so we can write this down. We have minus cosine of 2 beta, minus sine of 2 beta, minus sine of 2 beta, cosine of 2 beta. Lx is just 1, 0. And we do the matrix multiply. And what we have is minus cosine of 2 beta, minus sine of 2 beta. And notice the minus sign is common, so I'm going to pull it out. So we have cosine of 2 beta, sine of 2 beta. Minus 1, that's just a 180-degree phase, right? It's an overall phase. Let's throw it away. Okay. So let's draw what we just did in the XY plane. So our linear polarization state is, in the x direction here, right? And then what's the direction of our slow axis?
Rotated by an angle beta.
Rotated by beta. So I'll draw that as a dashed line. And now this linear state that goes out, where is it on that plot?
Oh, it's. Well, I mean, now it's got some y component to it.
So if I had, say, cosine of alpha, sine of alpha, what is that?
So it's on the circle around.
Isn't this just this, rotated alpha? Right?
Oh, X, Y, yeah, yeah.
Okay, so here, what is it?
Yeah, twice that.
So this is the output state, and it's rotated 2 times beta. So what is the effect of that halfway plate?
Just change the angle of the.
It just takes the linear instant state and flips it by beta about the slow axis. That's it. That's all it does. So if you're in the lab and you have a laser that's polarized, and hopefully all your lasers are polarized, and you have this optical table, you set up your laser, and you find that the linear polarization state coming out is parallel to the table, call it the x direction. But your setup, you need it to be in the y direction. What do?
45-degree angle halfway.
Grab a halfway plate, set it at 45 degrees, voila, now you have y polarized line.
Does it lose any power through that or no?
No, just for now reflections from the interfaces,
Okay,
but
but yeah.
if it's air coded, then you don't need to have that really. So, yeah, so halfway plates are awesome. If you have linear polarization states and you need it rotated to whatever angle, just stick a halfway plate in the system and rotate the halfway plate by half the angle you need rotation of. That's it. That's all there is to it. Okay. So, very useful components. All right, let's do another example with a halfway plate. Let's say that I have a halfway plate that is not rotated. And let's say that I come in, so this is a halfway plate. Let's say I come in with circularly polarized light in the clockwise direction. And I want to know what's the Jones vector that comes out. So the Jones vector that comes out is just the halfway plate matrix, which is -1, 0, 0, 1, since it's unrotated. And what's the Jones vector for clockwise circularly polarized light?
Or, so, still a 1/2.
Yeah. So 1/2.
I think it would be,
E to the J pi.
yeah.
Well, so what are the two things we need in order to have in order to have circular polarization?
Same magnitude.
Amplitudes are going to be equal, so let's just choose one.
Yeah.
And then what's the relative phase of the y to the x? Pi halves or minus pi halves. If we're clockwise, then it's pi halves. So we'd have 1 e to the j pi halves, which is just j. And then let's normalize it, so 1 over root 2. Okay? So we work that out. We have 1 over root 2, and it looks like we have what? That's what's that?
Minus 1, 0.
Minus 1 and
J.
J, yeah.
J. Hey. And the minus 1, let's pull the minus 1 out. So minus 1 times 1 over root 2, 1 minus J. Minus 1 is an overall phase, let's just toss it.
Oh, so it's the other direction now.
Yes. So this is circular counterclockwise.
So why do we put the normalization thing in there, just because, or?
You mean this thing?
Yeah, the one.
Yeah, just because, just to
Okay.
make it normalized Jones vector. Okay, so what's the effect of a halfway plate on circularly polarized light?
Versus its
Just flips it.
rotation.
Yeah, flips the rotation. That's it. So, quarter wave plates, or halfway plates rather, are really useful. Okay, so you think that's useful? Let's do quarter wave plates. Quarter wave plates are awesome. They are so useful. Okay, so quarter wave plate. Let's see how far we can get.
So each of these wave plates is only going to be good for whatever wavelength you're using, like, right?
Bingo.
Yeah.
Yes, it's wavelength dependent.
Yeah.
Yeah,
But if you're
because
all of a sudden using a different laser, you can't use like, unless it's the same wavelength, you couldn't use the same plates.
exactly. Yeah, you got to get different plates. Yeah. Unless you build something that is a variable retarder. We'll talk about how to do that. And then you have a wave plate for any occasion. You can set it to whatever you want. And of course, you're going to pay through the nose for that privilege. They're very expensive. But in some cases, they're worth the money. Okay, so here we're going to do a quarter wave plate for QWP. Okay, so in this case, the phase retardation is just pi halves instead of pi, like for a halfway plate. And so if we solved for the thickness, it would be lambda naught over 4, 1 over ns minus nf. I'm not going to bother doing a little bit of algebra. And so the Jones matrix for a quarter wave plate then would be e to the minus j, what? Pi over 4.
Yeah. That's, yeah, because we're over 2.
Yes, yes. E to the j pi over 4. Okay. Fine. And let's just immediately do an example. So let's say that we have z-axis here and our slow and fast axes for the quarter wave plate. And let's say that we have, here's the x-axis or x direction. Let's say we have linearly polarized light at 45 degrees. And we want to know what's the polarization state that comes out. So polarization state that comes out is the Jones matrix, which is, well, let's do it this way. W 0 quarter wave plate times this linearly polarized light at 45 degrees. We don't have a symbol for that. So let's just write it, 1 over root 2, 1, 1, right? So I have equal x and y components. There's no phase difference between them, therefore it's linearly polarized. Okay, so this would be e to the minus j, pi force, 0, 0, e to the j, pi force. Yeah, 1 over 2, 1, 1. And what do we get? 1 over root 2, e to the minus j, pi force, e to the j, pi force. Yeah, let's pull out this one right here. So that's e to the minus j, pi force, 1 over root 2. And that gives me a 1 there, and an e to the j pi halves there. this is an overall phase, let's throw it away. So we have 1 over root 2, 1j. What is that? Clockwise circularly polarized light. So we just took linear polarization and turned it into circular polarization. How cool is that? It just takes one component, quarter wave plane. And setting our instant linear state at 45 degrees with respect to the slow and fast axis.
What you could do with a halfway.
What's that?
What you could do with a halfway play.
Yeah, exactly. Yeah, you could start off with
You could
linear
just
and
rotate
x,
whatever your source
put a
is.
halfway plate, and rotate this to 45, and then, yeah. Okay, so let's say we do the same example, except the linear polarization state is at minus 45 degrees. So the only thing that's different is I have a minus sign right here, right? So minus sign, minus sign, minus sign, minus sign, minus sign, I get 1 over root 2, 1 minus j, or in other words, counterclockwise circular polarized light. Okay, so I can do either orientation, no problem. Circularly polarized light. Okay, and then as a final thing, and then I'm going to have to run to this conference call. Notice that this Jones matrix for a quarter wave plate, this unrotated Jones matrix, I could pull out the e to the minus j pi force, which would leave me with what? 1, 0, 0, j. Right? And this is an overall phase factor. I could throw it away. So 1, 0, 0, j. That is also a valid representation for the Jones matrix of a quarter wave plate. So sometimes it's more convenient to use this representation. Sometimes it's more convenient to use that representation. Just whatever. They'll always end up giving you the same result. Okay, so that brings us to applications of quarter wave plates, which I want to spend a little bit of time on because they're just so extraordinarily useful. And we don't have time to do it right now, so we will do that next time. Yeah, I know. Right up to the punchline and then, cliffhanger.
So would they be broadband
To be
steps
continued,
similar
it's like a
to,
soap opera.
T-line, would
This is a
it
good
be
fire.
tinier steps with different